Good afternoon, everyone. I'm Alessandro Trinca. I'm a postdoc at the University of Insubria on the beautiful Lake of Como in Italy. And for this last talk of the day, I'd like to dig a little bit deeper on what we can learn on this population of early massive black holes probed by JWST. And especially, I will try to give you some convincing arguments in favor of the evidence of a growth of this kind of object dominated by periods of super-Eddington accretion at early times. Now, as we heard extensively today, JWST enabled us to explore an unprecedented range of properties for this high redshift population of AGNs in terms of black hole mass, AGN luminosities, and also redshift. And we're starting to probe a regime where this black hole might still carry some information about their evolutionary environment. And what we're observing is that basically these sources are much more abundant than what was considered before the advent of JWST. And they're basically even a significant fraction of the galaxy population. So the idea is, can we leverage now this plethora of observation to try to constrain some information about the early mechanisms of formation of these first black holes and their accretion mechanism. And to do so, what we employ is the cosmic archaeology tool, which is a semi-analytical model tailored to reconstruct the early galaxy evolution in the first billion-year of cosmic history, and in particular, to follow the interplay between the central black holes and their host galaxy over a wide range of galaxy mass, resolving down to the first mini-halos, in order to provide a detailed modeling of the black hole seed formation. And this requires to resolve a number of physical processes which are partially listed down there. And with this model, what we are able to do is to follow the formation of both light seeds from POP3 remnant and heavy seeds from direct collapsed black holes, depending on the environmental condition of each system, and follow then their growth through accretion and mergers through cosmic times, obtaining large catalogs of AGN and galaxy population. And the strength of this model is its versatility, since what we can do is to probe what different accretion scenarios for the black hole growth at early times imply on the overall properties of this black hole and galaxy population. And what we've done in the beginning was to look, for instance, at what is the impact of different accretion scenarios on the typical distribution of black hole masses. And so here you can see how the black hole mass function changes across redshift if you assume, for instance, a standard Bondi accretion on the black hole limited at the Eddington rate, or if you consider on top of this model, if you allow the black hole to grow efficiently at high accretion rates up to the super-Eddington regime, but just for a short period of time, linked to the major interaction of its host galaxy, and in particular to major merger events for its host galaxy. And you can see how, of course, you have some differences in the overall evolution of the black hole mass, but of course you will have also a very strong impact on the black hole galaxy coevolution, so on the black hole galaxy scaling relations, as well as on the AGN luminosity distribution. So let's focus on the first one for the moment. And what we can do now is actually to compare the prediction of these models that were developed 2 years ago with all this data that we have from JWST. And especially because, as we heard a lot today, this population of early black holes seems to be very overmassive in terms of black hole mass over stellar mass when compared to a local scaling relation. And you can see there basically the population of objects observed with JWST, and also this potential analogous sample which has been observed now down to cosmic noon. And of course there are some caveats on this population, since there might be just the tip of the iceberg of their underlying black hole population, and there might be some uncertainties on the estimation of the black hole mass as well as the stellar mass, and I will touch briefly on that on the end of the talk. But let's take these properties at face value and compare them with the prediction of our models. And you can see that we achieve an extremely nice agreement. You see this surprising alignment with the model where we actually assume the black hole growth to be dominated by this short period of accretion linked to the major interaction of their host galaxies. So this model that we've done is, has a pretty simplistic approach, but seems to be telling us something on the early evolution of these objects. So what we can try to do is to see what are the implications for the evolution of this black hole population. And so what we can do is actually what we've done is to select a subsample of these systems such that they're basically overmassive in terms of black hole mass over stellar mass, but more consistent with the local scaling relation in terms of black hole mass over dynamical mass, such as has been suggested by observations. And we can color code them based on the fact that they're descending from light or heavy black hole seeds in the beginning. And we can track back the evolution of both the black hole component and the stellar mass component to see what are the implications for the evolution. So if we look at the evolutionary tracks of the black holes, of the black hole population, you can see here again the same color coding for black hole coming from heavy seeds and light seed. You see that basically the pathway of evolution are very similar, since in this case is the accretion scenario that is dominating the evolution of this system more than the original seeding channel. And we can ask ourselves, what are the typical accretion timescale that this system seems to have? Or better, how sustained this period of superred internal accretion has to be in order to match the observed properties. And you can see how the duration of the single burst of accretion seems to be between 0.5 and 3 million years in our model, but of course they have to go through repeated episodes of superred internal accretion to build up the observed black hole mass. And if you look at the overall duty cycle, so the total time that they spend in this phase of efficient accretion over the total cosmic time of the moment of observation, you see that we have pretty low duty cycles, between 1 and 3% for the bulk of the population, and up to 6% for the more massive systems. So this is what concerns basically the evolution of the black hole, but what about instead the building up of the stellar mass in these systems? Well, what we can do is to try to understand how much the black hole co-evolves actually with the stellar mass of this system. And so track the fraction of the overall stellar mass which has been gathered, which has been assembled in the same galaxy where the black hole was evolving during cosmic times. And you can see, so basically dividing the evolution in a synchronous evolution and an asynchronous evolution between the black hole and the bulk of the stellar mass. And what we find is basically there is a tight spread in the average evolution, so all these systems seems to go through a similar evolutionary path, and typically before redshift 8, we have that the black hole is evolving in a small system with a lot of dynamical interaction, so it grows very efficiently, exerting a strong feedback on its environment, and the black hole over mass ratio can grow even higher than what we're detecting. But then, after a certain threshold, which is around redshift 8 for this population, the real black hole galaxy coevolution starts to build up, the system is growing, and the vast majority of the final stellar mass is gathered in this final 300 or 400 million years of evolution. So the galaxy is actually catching up with the black hole mass. But what then? Because we do not seem to observe similar system in the local universe, so how do they get closer to the local scaling relation? Unfortunately, our model stops at redshift 4, so we cannot trace forward in time the evolution of these peculiar systems, but we can focus on a single interesting case observed at higher redshift, which is this very massive dormant black hole observed with jades at redshift 7. And as you can see, this has a very high black hole over stellar mass ratio. And what we can do is basically the same. So try to reconstruct all the best synthetic counterparts of our object at the moment of observation, trace back in time their star formation history of these counterparts, and check, as a consistency check, if they're actually matching what has been predicted by the self-fitting model. And you can see how all our evolutionary history are pretty consistent with at least what has been inferred from bagpipes. But in this case, we can track forward in time the evolution of these systems, and you can see how as soon as the system do not encounter strong dynamical interaction, you can see the major merger of this system signed by the vertical lines. The star formation rate of the galaxy might rise very quickly up to a 1 order of magnitude. And if we look at this peculiar evolutionary case, the stellar mass increased of 1 order of magnitude by the time the galaxy evolved down to redshift 4, so pushing the system closer to the local scaling. And since you would expect the typical rate of merger-merger events to slow down with redshift, this is kind of giving you a natural way to explain why these systems are approaching the local scaling relation at, let's say, in the local universe. But of course, this is mostly on what concerns the black hole galaxy scaling relation, but I also briefly mentioned the impact that this kind of accretion history might have on the luminosity properties of the AGN population. And what we originally found in our model was that if you look at the luminosity function of AGNs, here you have it between redshift 5 and 6, when you account for this short burst of efficient accretion for the AGNs, this kind of bump appear in the luminosity function in the bright end. And we were a bit surprised by this peculiar feature in the beginning, but then now that we have data, we realize that if we overplot the bolometric luminosity function, if you believe the bolometric luminosity of little red dots on top of this, but please, if you believe it, let's assume that we believe it. But still, you see, this nice agreement with the data. Still, of course, there is a lot of uncertainties here on the data, but this feature seems to be reproduced. And this is because actually, this feature is given by smaller black holes that are switching on and off, populating the bright end of the luminosity function, but with a number density which is representative of their typical mass, which is smaller, which came from the low mass end of the mass function. And at the same time, this kind of bursty evolution for these early black holes give you a sort of bimodal distribution for the population of detectable AGNs. And you can see that here when you have the luminosity of the AGNs as a function of the black hole mass, and the color coding in the plane is given by the expected completeness of observations. And you can see that basically the JWST service should be sensitive mostly to lower mass black hole, but accretively very efficiently matching the region of the plane where we have these data points, which are the JWST observation. Or if you want to look at the population of the underlying population of dormant black holes, you have to go to very high masses, such as this single observation of a dormant black hole at redshift 7. And before concluding, let me just touch an additional point, which is the fact that if we assume this system to be accreting at super Eddington rates, there might be a systematic overestimation of their mass, relying on the standard single epoch method. And this is because reverberation mapping campaign showed that you have a dependency basically on the size of the broadline region with the Eddington ratio. So since basically the broadline region shrinks at higher Eddington regimes due to the self-shadowing of the slim disk, which is puffing up, going toward higher accretion rates, sorry. And what we wanted to do in this recent work is to try to understand which is the impact of this effect on the population of black holes observed with JWST. And we built a simple semi-empirical model taking into account for this effect of self-shadowing, and we give as an input of an MCMC the properties of the broad emission lines observed with JWST for this population of massive black holes, and explore the parameter space in terms of black hole mass and Eddington ratio to understand which are the favored values by the MCMC. And what we find is that actually lower black hole mass and higher accretion rate are preferred by the model. And if we translate this in the scaling relation, you can see with respect to the black hole mass value that you would extract from the standard single epoch estimation, our estimations are quite low, and at least for some of these systems, this might relieve the tension of having these extremely overmassive black holes with respect to the stellar mass. So still, you have a very massive population, but for the more extreme system, this might be relieved. So I leave you with my conclusion. I hope I give you at least some interesting insight on why super Eddington accretion might, at the same time, explain a lot of these strange features that we're observing for this population of massive black hole at high redshift. Thanks a lot for the attention.
Thanks for a nice talk. So let's see if I can push back against the massive seed lobby, which is dangerous because they're very powerful. So why can't you, if you just let all of the accretion be super Eddington, or I guess I would prefer to say supercritical, but just so that now the seeds are 100 solar masses, but you allow a very flexible model, which you have. What breaks, what observations can you not reproduce? Is it the overmassiveness, or?
I mean, the point
in other words,
here,
can I explain all the data to date with just regular seeds, but just allowing the radius of efficiency to be very small?
Yeah. I mean, the point here, the important point is that depends on, I mean, what we assume here is that the period, the super Eddington growth, is strictly linked to period of enhanced dynamical interaction of the galaxy. Because if you just allow all your black holes to grow at super Eddington rates, your lighter seeds are not able to grow at all, just because if you assume the standard boundary accretion, you cannot make it to, manage to grow them in time. And on the other side, you would expect a very strong feedback from your more massive black holes if you just allow a super Eddington growth for all their evolutionary time. While if you just assume this first phases of efficient accretion during major mergers, you'll have in one side this very efficient growth on the black hole in the early phases of evolution, which matches very well this overmassiveness. And then on the other side, you have also a natural way of explaining why then they stop to accrete so efficiently at lower times, and why we do not observe similar system in the local universe. Because you would expect the rate of major interaction of the galaxy to slow down with time and the galaxy to grow inside. So the major interaction of this galaxy wouldn't be able at that point to trigger strongly inflow of gas anymore in the center and being able to reactivate this central black hole so efficiently.
Thanks.
A bit on this in particular. So I'm part of the lobby of intermediate masses, so I think I'm the poorest in this room. So it's something that I think is important to mention for the light seeds is dynamics. So if you're forming a black hole with a mass of 100 solar masses in a galaxy, it just moves around in random directions, so it doesn't stay where dense gas is. It doesn't accrete. So it's much harder to grow a light seed than a heavy seed just because of dynamical considerations that have not been discussed much here. And we can talk later if you want.
I think I had a slide.
Yeah, exactly.
So please use the microphone.
But I haven't finished.
Yeah.
I actually have a question.
Yeah.
So this was just, I have a question for Alessandro first. We can discuss this later. So I think you said, no, it was not on this slide, but you said that since there is strong feedback, the black hole stellar mass relation can grow even higher than C. So does it mean that agent feedback affects star formation without affecting the black hole growth itself?
Yeah, basically, yeah, what we find is that the idea is that typically you need to, I mean, you have to explain why you're growing the black hole so quickly and you're not growing the stellar mass in this case, and so you build up this very high black hole over stellar mass relation. What we see for this population with this model, which is at the moment pretty simplified, but seems to catch up something very interesting on the physics of the evolution, is that on early times you have this smaller system. So as soon as the black hole is actually lightened up by this strong inflow of gas, its feedback is actually efficient on the galaxy, evacuating the gas very efficiently and halting the star formation on the smaller system. As soon as the black holes start to be in a more massive system, a more massive galaxy, the feedback is still there, but start to be weaker, and the galaxy can actually build up the most of its mass in the final few 100 million years of evolution. So basically what you have is a sort of black hole dominance when, due to peculiar evolutionary history, you might grow very efficiently at early times this black hole with this short burst of evolution, but then the galaxy, while the system is growing up, catches up with the building up of the stellar mass. You're not convinced by this?
I think that my question was, why isn't the AGN feedback affecting its own growth? So I understand,
sure.
you know, stopping
sure.
formation, but on scales of the boundary radius.
No, because what we are assuming in this simplified model is then when you have a major merger, we assume a fraction of the available gas able to go into the black hole on a typical timescale which is linked to the dynamical time of the galaxy, up to the point in which basically you have or no more gas, or basically you exceeded a given fraction of the overall time of the galaxy, for which you would expect it to be again relaxed. So basically this is linked, this is important, that it is linked to the assumption that we're doing here. If we assume basically just a standard Bondi accretion, even if we allow the black hole to go through Eddington, we are not able to reconstruct this feature. We need the black hole growth to be dominated by a very short period of time in which you can trigger this strong inflow of gas toward the black hole without relying on the standard Bondi accretion. Kind of, yeah.
So just to quickly comment on the idea of, so the Renaissance simulations by John Wise and collaborators, they found they tracked about 15,000 population 3 light seeds at redshifts of 15, 10, 11, and 9. And they find that, as Martha mentioned, these light seeds are never quite in the right place. They get jostled around, and they are very rarely, out of the 15,000, a handful, like literally 20 of them, were in dense enough regions where they would grow fast enough to actually become supermassive.
Why do you think you know the density at percent of the parsec scales?
No, but obviously this is all resolution limited, but these are the cosmological simulations that reproduce, you know, other observables at later times, right? So yes, they are of course limited by their resolution, but these are the highest resolution we can do right now. So
I told you they were powerful.
We're starting to get into more general discussion. So let's actually thank Alessandro and then